In this example, we are going to be looking at this series right here, and we're going to be checking to see if it converges based on the alternating series test. The alternating series test says if you have an alternating series in this form, so that means we have a factor of -1 raised to some power, and this is where we're going to get the alternating signs from, times some bn. In this case, we're using k's instead of n, so think of this as bk. And this represents some sequence of terms. All right, and so if we have an alternating series, this test tells us it converges if these two conditions are met. So the first condition is to check to see if the nth plus 1 term, or in this case the k plus 1 term, is smaller than the kn term. So we're looking to see if this sequence is decreasing. The second condition that needs to be met is that the limit of that sequence, so that's the part without the -1. So we're looking at the absolute value of this expression. When we look at just the bk term, if we take the limit as k goes to infinity, we're checking to see if that goes to 0. So these are the two conditions that we need to check. If these two conditions are met, then we can say by the alternating series test, the series converges. So checking the first condition. If I plug in and replace all my k's with k plus 1, that will give me my k plus 1 term. So I'm looking to see if my k plus 1 term is smaller than my k term for all k greater than or equal to 4. Now, I'm choosing k is greater than or equal to 4 because that is where this series starts. Okay, so we have 4 to infinity here. Now, I'm sure there's a way that you can prove this algebraically. I'm a very visual person, so I looked at the graph using GeoGebra, and the k plus 1, that's here in the green, and I used x's when I graphed it, but just keep in mind that those x's are like the k's. And also keep in mind that these are continuous curves here. And so we're really just looking at the integers. K is equal to 4, k is equal to 5, k is equal to 6, etc. So keep that in mind when you're looking at this graph. So our k plus 1 term is in the green, so that's this one here, and our k term is in the blue. So if I look at this for all the values greater than or equal to 4, so I'm looking at it from here over, every single value I notice the green after this 4, the green is always below the blue. And if you go out further and further and you zoom in, you can check it. So for all values, for k is equal to 4 or greater, you can see that the k plus 1 term is smaller than the k term. So we can verify that and say, yes, these terms are smaller than these terms. So the first condition is met. And like I said again, I'm sure if you goof around with this, there's a way that you can show it algebraically, just like looking at graphs. Now, looking at the second condition, we need to show that that sequence, the part that doesn't have the -1 factor in it, that approaches 0 when k approaches infinity. So I need to show that the limit as k goes to infinity of k to the 3rd over the square root of k to the 8th plus 1 is equal to 0. So I want to use some algebra to rearrange this to get it in a form that makes it easier to see if it goes to 0. So what I did is underneath the square root, I divided everything by k to the 8th. However, if I want to divide the top by something, and I have to make sure it's the same expression on the top and the bottom, if k to the 8th is under the square root, then outside the square root, it's k to the 4th. So the top, I'm going to divide by k to the fourth. The bottom, I divide by k to the fourth, but when it comes inside the square root, it's k to the eighth. So really, I'm dividing everything by k to the fourth, just keeping track of what that would be when I bring it inside the square root. And so on the top, I get 1 over k. On the bottom, I get the square root of 1 plus 1 over k to the eighth. Now, when I take the limit as x or as k goes to infinity, this goes to 0. This goes to 0, so I'm left with 0 over the square root of 1, which is 0. So because we proved both conditions hold true, we have shown then that the series converges based on the alternating series test.